Hello there, Mr. Sutton here, bringing you the Algebra 2 9-4 lesson on experimental design. In this one, we will be assessing the validity of an experiment's results, designing experiments and/or observational studies, and also analyzing experimental designs to see what the flaws are and what we can do to improve them. Before we start going through and assessing validity of experiments and all those wonderful things, let's go through a few terms so that we're speaking the same language. So what we're going to be seeing in this lesson are examples of a few what are called controlled experiments. Controlled experiments are basically experiments where you're studying groups that have the same conditions except for one or more specific variables. So they're controlled in the respect that you're trying to eliminate all these other variables that might be impacting things and just kind of narrow it down to one or two things that are changing between the two groups. Now, speaking of the two groups, one of those groups we call the treatment group. This is the group that's given the treatment, whatever that is, either a medicine or a procedure or some characteristic that you're observing that you think is important. And then the other group is called the control group. This is the group that is given no treatment. It's the quote-unquote normal group. And in addition to being given no treatment, another alternative is your control group might be given what is called a placebo, which is basically a fake treatment. For example, if there's some headache pills that you're giving two different groups, you might give one group some basically what are sugar pills that they think are headache pills but really aren't. There's amazing brain-body kind of connections. So we have observed that sometimes people will feel better, just because they think they're taking something that'll make them feel better, not because they actually are. Kind of crazy, but that's one of the things that we have to control for. Now, when we're choosing these two groups, it's kind of important how we do the choosing. A randomized comparative experiment is one in which the subjects are, well, as the name suggests, randomly assigned to the treatment and control groups. If we do this, then we can then determine the effects of the treatment by comparing these two groups. Now, the randomization is important. Randomization, as we've seen in other lessons, reduces the potential for bias. On the other hand, if you just let people choose which groups they go into, self-selection of this kind increases opportunities for bias. And we might be introducing other variables that we were not accounting for if we're letting people self-select. For this reason, conclusions that you reach from a non-randomized, more self-selected experiment may not be valid. They're not necessarily invalid, but they have kind of a higher bar that they have to pass to be considered valid. So when we are assessing the validity of an experiment, randomization versus self-selection is definitely at the top of the list of things that we look for. So with all that in mind, let's take a look at some experiments. So for each of the next two experiments, you're going to determine whether the study is a randomized comparative experiment. And if it is, describe the treatment. What's the treatment group and what's the control group? If it's not a randomized experiment, explain why not, and then discuss whether the conclusions drawn from the study are still valid. So our first example is this claim here by a health clinic that vitamin C lowers cholesterol. So at a health clinic, patients were given the choice of whether to take a dietary supplement of 500 milligrams of vitamin C each day. 50 patients took the supplement, were monitored for a year, and 50 patients did not take it and were also monitored. At the end of 1 year, the patients who took the supplement had 15% lower cholesterol levels than the patients in the other group. So again, is it randomized? And if it is, what's the treatment group, and the control group? If it's not, why not? And are the conclusions valid? Pause the video and give that some thought. All right, so let's take a look at this one here. Now, because the patients were given the choice whether to take the dietary supplement or not, the groups, the control versus the treatment, were self-selected. So because of that, this is not randomized. Again, the groups were self-selected, not randomly chosen. Because of this lack of randomization, the conclusions may not be valid. And just to go a little bit further on that, one kind of just playing devil's advocate counter argument to this idea that the supplements cause this 15% lower cholesterol level. What if it wasn't the supplements, but the fact that the people who chose to take the vitamin C, maybe they were more health conscious to begin with, and that's why they chose to take the vitamin C. And maybe because of their health consciousness, they did other things that caused this drop in cholesterol levels. So again, because it was not randomly chosen, we can't really exclude that possibility. For this next experiment, to test its new touchscreen kiosks, that's this thing kind of here, a restaurant randomly selects and divides 186 customers into two groups. One group uses the new touchscreens and the other group just orders at the counter. And they notice that users at the new touchscreen kiosks received their food orders 25% faster. So first off, is this a randomized study? Well, it looks like it is. It literally says the restaurant randomly selected and divided all these people into two groups. So this is randomized. That means that we can talk about a treatment group, and a control group. The treatment in this case, it seems kind of funny to call it that, but the treatment was the touchscreens. And the treatment group are the customers who got to use the touchscreens, and the control group were the customers who just went to the counter. So those last two examples were experiments, and experiments are great for trying to figure out the connection between different variables, but they're not the only option. We also have simulations, surveys, and we'll also talk about specifically on this slide, observational studies. And we often have to choose between these things to see what's the best option for studying variables. Now, before we really talk into the pros and cons of each of these, I need to introduce another concept in here. When we're studying the connection between variables, we might at some point notice that a change in one variable happens to accompany a change in another variable. This is the idea of correlation. Again, that a change in one variable accompanies a change in another. Now, it could be that it's just a coincidence, or it could be a little bit more. It could be that there's a relationship called causation, where a change in one variable is actually causing a change in another. So often we do these studies and we see that there's a correlation, and then we dig a little deeper and see if we can prove that there's a causation. And we do have to do that proving because just because there's a correlation, just because two variables happen at the same time to change, that does not imply that there's a causation, that one is actually the cause of the other's change. There could be a third variable for which these two initial variables are just kind of a side effect, and because they have the same cause, they're happening at the same time. Sort of a classic example of this is the connection between ice cream sales and drowning. It is a recorded statistical fact that as ice cream sales increase, so do incidents of drowning. Now, is this because eating ice cream makes people drown? Definitely wouldn't be the other way around, right? Well, it turns out that, both of these things could be happening just because it's getting hotter during the summer months, causing more people to eat ice cream and also go swimming, which of course increases the risk of drowning. So again, correlation, causation, they don't necessarily imply the same thing. So to kind of tease out this difference, we have to dig a little bit deeper into the relationship between experiments and observational studies. So with an experiment, the way that we design one of these, just to kind of review, and it's good to know anyway, is again, we randomly assign our treatment and control groups, we apply the treatment, and we record the results. With an observational study, in contrast, we're not actually applying anything, so we don't really assign people to control groups or treatment groups at all. Instead, we randomly choose to observe people who have the variable that we're looking for. We call them the treatment group, and those who don't have that same variable, we call those the control group. So just to piggyback off of that somewhat morbid example earlier with the ice cream and the drowning, we're not giving people ice cream and making them drown. We're just watching people who fall into those two categories and hopefully trying to save the ones who are drowning, possibly also the ones who are buying the ice cream. In any case, once we've chosen to observe these different groups and hopefully randomly chosen people from each group so it doesn't bias things, we just watch and record the outcomes. Now, there's different pros and cons for each of these two ways of doing things. With the experiment, you can control for the variables. You have a lot more control than experiment. And because of this, you can kind of isolate the variables that you're interested in and have a better chance of showing causation. You have a better chance of ruling out that mysterious third variable that might be accounting for your correlation. Given all things being equal, an experiment is going to be the best option if you're actually trying to prove causation. Unfortunately, experiments do have some downsides. So the treatment that you're applying in an experiment might be unethical. Again, drowning people, not okay. It might be too expensive. Like if you're trying to study the effects of winning the lottery on people's happiness, you can't just go around handing out, $1 million or $1 billion paychecks to people. And your treatment might be actually impossible. If you're trying to study the effects of natural disasters like earthquakes on how people treat each other, well, you don't really have it in your power to cause an earthquake. And even if you did, that would probably be unethical and expensive. So experiments do have their limitations. With an observational study, we kind of fill in the gaps left by experiments. So although we can't, directly apply a lot of these treatments, with a study, an observational study, you can study these treatments that are already kind of affecting people, and that gives you a way to study them in a way that experiments can't. So you can still measure the effects of things. The difference is you're not directly causing the effects. You're just looking at these effects that were going to happen anyway and seeing what results from them. There is a con, though. You do lose something for this increased flexibility with your observational studies, and that is because since you have less control, you're usually only able to show correlation, not causation. You don't have enough control to really rule out those other hidden variables. So we pick experiments when we can, but when we can't, we settle for an observational study. So as a follow-up to our discussion on experiments versus observational studies, for these two examples here, let's say that we're trying to determine whether each of these research topics is best investigated through an experiment or an observational study. So lots of things to consider. And then, whichever one it is, describe the design of the study. So pause the video and try out each of these ones. Figure out if it's better with an experiment or an observation, and then how would you design it? All right, let's look at our first one. Does practicing yoga result in fewer falls for older people? So first question is experiment or observational study. Well, the experiment would involve actually making older people do yoga, which might be harmful depending on what their health condition is. So that means an observational study would be a better fit for this. An experiment might not be ethical, might cause harm to people. So we don't want to do that. Instead, using an observational study, we would just identify a treatment group that's already practicing yoga, like these fine folks up here, a control group that doesn't, and then monitor both groups for numbers of falls. And of course, you would also try to take into account lots of other things in their environment and lifestyles to make sure that other variables weren't clouding the picture, but there's only so much you can do. Now, for this other example, does listening to jazz music improve a person's ability to memorize a list? So although you could do an observational study of people who listen to jazz and people who don't, and take a look at their test scores, you do have a little bit more of an option on this one. I mean, contrary to what some people might think, it is not unethical to have people listen to jazz music, so you actually could do an experiment on this one. Your experiment could take the form of randomly selecting a treatment group that listens to jazz, a control group that doesn't, and then giving both a memorization test. So in a moment, we are going to be taking a look at some experiments, and what we're saying here also can apply to observational studies as well. And we're going to basically analyze them to see what are the problems with them and how could we fix those. So just to get your creative juices flowing, here are some common design flaws and solutions we could employ for them. So you can apply these in whatever situation you deem necessary. So one problem is that you might have a small sample size. if your study doesn't include enough people, then the changes, the effects you're seeing might be due to random chance and not anything actually significant. So a way to fix this is just to increase the sample size. So how big is big enough? Well, it's going to depend on what you're trying to measure. Probably a sample size of 5 people is not great. A sample size of 10,000 people is pretty good. So I guess the lesson here is just get as many people as you efficiently can. Now, another problem we run into with some experiments is that there's no comparison made to the control group. And, so kind of one example of this might be somebody who's trying to promote their dieting program, and they say, hey, the people who were on our diet lost an average of 10 pounds over 5 weeks. Well, that's great. But how about the people who are in a similar kind of environment who didn't do your diet? If they also lost the same amount of weight, then maybe your diet isn't really all it's cracked up to be. So a solution to this problem is just to, hey, compare your treatment and your control group. If nothing else, this can at least account for the placebo effect. Another problem we run into is self-selecting groups, and we saw this earlier. If you just allow people to choose whether they do a treatment or not, then there might be factors like them being health conscious or other things that impact the survey. So the solution to the self-selection problem is to randomize the group assignment. And another issue that sometimes presents a problem is if your groups, your control and your treatment groups, have different environments. That's introducing other variables other than the one you might actually be testing for. So one way you might be able to fix this, and it might be feasible or not, but you can try to reassign the groups to get a similar mix of environments in both groups. For an experiment, you might actually tell people, hey, go to this other living situation, and maybe if you're paying them enough, they'll do it for you. If it's a study, then you can just change which people you put into which groups. For our last problem with this whole design analysis sort of thing we're doing, we're going to take a look at a pharmaceutical company that wants to test the effectiveness of a new chewing gum designed to help people lose weight. Imagine that. So for each of these 3 different designs, 3 different experimental designs, we're going to identify a potential problem. If it exists, it might not. And then if there is a problem, describe how we could fix it. And maybe we'll get a hefty consulting fee for doing this, but probably not. So take a look at this first one. So the company randomly selects 10 people who are overweight. 5 subjects are randomly assigned to receive the new chewing gum, and the other 5 receive the placebo. After 3 months, each subject is evaluated, and it's determined the 5 subjects who have been using the new chewing gum have lost weight. So pause the video and kind of think about this in light of what we said about potential design flaws, and see if you can come up with what the issues are here, if any. All right, so let's take a look at each piece of this. One thing the company did right was randomly selecting the people and randomly assigning them. So that's a good thing. We like to see random comparative studies. One potential issue, though, only 10 people? So that is a small sample size, very small sample size. Whatever changes we see could be due completely to chance. There was another issue as well, though it's a little tougher to pick up on. They said after 3 months, each subject is evaluated, and it's determined that the 5 subjects who have been using the new chewing gum have lost weight. Well, that's great, but what about the 5 subjects who did not use the new chewing gum? What happened to them? It's kind of hard to tell by the wording of this, but it looks like we didn't even look at them, and that's a problem. It looks like there's no comparison to the control group to account for a potential placebo effect. So, potential fixes for this: increase the number of people in the study, include more people in the study, and for this second issue, maybe actually compare the results of your 2 groups that you took the trouble to organize. Alrighty, so we have the same pharmaceutical company with its weight loss chewing gum, and here's another person trying it out. Here's 2 more different studies that they set up involving this question. Pause the video, read through each situation, and lend your insight on what you think about the design of these experiments. All right, let's look at experiment B. So the company randomly selects 10,000 people who are overweight. Subjects are divided into groups according to where they live. Subjects who live in a city receive the new gum, and those who are in rural areas get a placebo. After 3 months, a significantly large number of the subjects who live in a city have lost weight. All right, so things that the company did right this time around. So the random selection of the 10,000 people was good. The fact that it was 10,000 people, we've got a larger sample size, so that's a huge improvement on experiment A. There is an issue though, and that's that the two groups are in different environments. So the treatment and control group environments being different is a bit of an issue. And the part of the reason this is an issue is you have a different lifestyle possibly depending on where you live. If you're in a city, there's a better chance that you're not driving everywhere. You're probably walking a lot more because driving is a pain in the city. So you might be walking more, and because of that, your weight loss might be due to where you live. Another potential problem with this study, although the wording again makes it a little bit tricky to see if this is really an issue, they said a significantly large number of people in the city have lost weight, but again, they didn't really say how that compared to the people in the rural areas who are getting the placebo. So again, doing a direct comparison of those would be helpful. But to speak to this environmental issue, one solution would be to include equal numbers of rural and city dwellers in the two groups that you're observing. You don't actually have to make them move, but maybe just give half the people in the cities the chewing gum and half the people in the rural areas the chewing gum, and half not get it. All right, so now looking at experiment C here, company randomly selects 10,000 people who are overweight. The subjects are divided into groups according to age, and within each age group, randomly assigned to receive the new gum or placebo. After 3 months, a significantly large number of the subjects who received the new chewing gum have lost weight. So we're liking this a lot better. Again, just kind of ignoring whether they did the comparison to the placebo group or not. Let's assume they did, because they've been wording it the same way this whole time. So we've got a large sample size, we've got random selection, and because we've got these age groups who are randomly assigned to get the gum or not, we've kind of accounted for all the differences that we could have within the different groups. So because of this, we would say that there's no real problems with this. A large sample size and similar randomized groups makes this a much happier experiment. So this is the end of our lesson on experimental design. I'm not sure at the end of the day if chewing gum actually can help you lose weight, but perhaps doing problems about whether chewing gum helps you lose weight can at least make you better at statistics. Until next time, Mr. Sutton signing off.